Okay, on to acid and base. I wanted to briefly remind you to know the values of our standard pH, 7.4. Anything above that would be alkalosis. Anything below that would be acidosis. You should know that pH is equal to bicarb over CO2 or kidneys over lungs. That will help you understand when it's respiratory versus metabolic. If our bicarb is changing above or below 24, then we know that it's a metabolic condition. If our CO2 is changing above or below 40, then we know it's a respiratory condition. I wouldn't worry too much about memorizing the compensation values. By that I mean it increases by 1 for every 3.5 that it's in your lab. Those values will be provided. I would just know the 24 and 40 and your standard pH value. I would also memorize the anion gap equation. I would memorize what the anion gap is, what things change it. I would remember the standard sodium concentration, which is 140, as well as the chloride concentration, which is 104. That's about all I would know. I would make sure you know your lab, the acid-base lab, inside and out. Be able to answer any question in there. If you have questions, reach out to me. I can answer them the best to the best of my ability. I would know that some of the common causes of metabolic alkalosis and acidosis. Make sure you know those. I wanted to move on to to explain our hyperkalemia, hypokalemia, what that leads to. I would memorize that hyperkalemia, I'm going to abbreviate hyperpotassium, is equal to acidosis. I would know that this is hypoexcitable, while the opposite is true of hypokalemia. Alkalosis is equal to hypokalemia, and that is hyperexcitable. And we can explain it with these cells. So if we have a ton of potassium out here in our hyperkalemia, right, we're going to want to compensate for that. So initially, we are alkalotic, but as we start to change that by pumping potassiums back into the cell, we're going to have this antiporter with our protons, and we're going to become acidotic. If you remember, these protons will go and compete for a binding site on albumin with calcium. Okay, so if our hydrogen ions come in and we kick off calcium, our protons are going to bind to albumin. We're going to have a bunch of free calcium in our cells. Do you remember what calcium does? Calcium causes those gates, the sodium or our sodium channels, to struggle to open. Remember, it pushes on it and it doesn't open as well. Therefore, we're going to be hypoexcitable. The opposite is true of hypokalemia. So if we're hypokalemic, we're going to want to kick a bunch of potassium to the outside of the cell, and a bunch of acid is going to come in. Those protons are going to come in. If we lose protons in the extracellular space, more calcium is going to be able to bind to albumin. If we take more calcium and bind it to albumin, then we don't have enough calcium to push on those gates, so they open easier. And then we get hyperexcitability, right? Remember Hunt's story where he was sick and he was having spastic contractions in his muscles. That was because he was hypokalemic. That's about all I would remember. Make sure you know hyperkalemia is equal to acidosis, which is equal to hypoexcitability, and the opposite is true of hypokalemia. Hypokalemia is equal to alkalosis, which is equal to hyperexcitability.